Can you see us?
Yeah.
Yeah. Okay. So we start our seminar today. It's in-person seminar, and our speaker is the Luca Maffioli from Melbourne. And Luca will explain what he's doing and in Melbourne and why he's in the UK now. Before we start the seminar, let me remind you change. First, it's a new seminar. It will be on 4th of April. It will be in person and advertised in this room.
Size 031.
031. Okay, it's downstairs. That is will be a seminar. It was not so much for public, so there will be no online participants. It's for presentations by Chunhao Wang, our PhD student, and Daniel Netherwood. They are coming to BMC with oral presentations, and on 4th April, 1 week before the BMC, they will make presentations here. So please attend their presentation and to help them to improve their presentation and their presentations. Okay, so and then on again next on 25th we have a seminar from Twente. Nothing on 2nd May. On 9th will be seminar will be talk from Cardiff, and on 16th May from Seville is by Jose Gardilia. By the way, he is editor of Journal of Fluid Mechanics. Please attend. I don't think so. I don't think so, but it would be good if you'll come here. Then we could show here our hospitality. And then on next 23rd, it will be a presentation by Oleg Marchenko from Kiev. He is attending us now. And on 30th, last seminar, it's by Sebekov, also from Kiev. There will be this presentation. Potentially, we can go beyond that. Yeah, so far we stop at the 30th of May. So Luca, welcome to Norwich. I understand it's first time.
Yes.
Yeah. And you are just a few hours here, so
yeah. 2 hours.
2 hours.
Less.
To be exact, so you can see it will be a mathematical presentation. It's very rigorous. And please explain your project and what you are doing in Melbourne, what you are doing in Imperial, and start your presentation.
Thanks.
45, 50 minutes.
Okay, thank you. Thank you very much. Okay, good afternoon, everyone. I'm Luca Maffioli. I'm working as a postdoc at Swinburne University of Technology in Melbourne with Professor Billy Todd, who is also the supervisor of my PhD that I got last year. So the project that I'm working on is the study of new lubricants using molecular dynamic simulations. In particular, we want to measure the friction coefficient at the fluid-solid interface in nano device application, these kind of things. And I'm spending a few weeks here at Imperial College working with Professor Daniele Dini in the mechanical engineering department at Imperial College London. I will stay here about another month. This presentation is mainly, we can say, methodological in the sense that I will show you the results that we recently found and we submitted to a journal about a month ago, which regard a method to measure any quantity in general, but in particular the shear pressure and the slip velocity at the interface between fluid and solid in microscopic system using molecular dynamics simulation. This method is called the Transient Time Correlation Function. Now, since maybe some of you are not very familiar with about what molecular dynamics is, I will just give you a very quick hints about what molecular dynamics is, or at least the central gist, just to give you an idea. So molecular dynamics the molecular dynamics is a set of numerical techniques. So we are talking about numerical simulations, computer simulations, in which you study the properties of system composed by a great number of particles by investigating the dynamics of each single particle composing the system. That is, you follow the trajectory by integrating the equations of motion, numerically, of course, the equations of motion describing the dynamic of each particle inside the system. So what's the, let's say, advantage of this approach? Well, for one, of course, you need to use this approach when, for instance, you have microscopic systems composed maybe by hundreds, thousands of particles, but that are well, let's say, below the level at which you can use, for example, continuum mechanics. I can think of, for instance, carbon nanotubes that are microscopic structures, we can say pipes, nanochannels, nanotubes, made of one single layer of carbon atoms, or carbon molecules, we can say, and which are as thick as few atoms diameter. As you can imagine, continuum mechanics hardly can be applied on this kind of systems. And in general, you can study the rheology of materials with very complex constitutive relations. So again, for materials for which the constitutive relation, and so for which continuum mechanics has not been established yet, because the rheology is very complex. Or in general, you can study, and this regards, let's say, we can say the the technological approach, let's say the technological standpoint. Or you can explicitly investigate more complex structures like biological proteins. For instance, you can study the protein folding, the DNA folding, and so on. And if I'm not mistaken, a few years ago, they even simulated an entire virus. I don't remember the name now, but I can give you, if you're interested, some ideas about that. They simulated, using molecular dynamics techniques, an entire virus from the atoms composing the virus. So they simulated each atom composing the virus, and they have seen how this virus behaves and evolves and so on. So this is just a quick glance of where you can apply molecular dynamics techniques. My specific field is to study, in particular, the rheology of materials. So I'm let's say, focusing mainly on the statistical mechanical approach and on the tribology approach and so on. So the central idea of molecular dynamics is this. As we said before, it's a computer technique in which you initialize the system, the system that you want to investigate. That is, you assign to each particle. When I say particle, I mean either molecule or atom. For me, particle has a generic meaning. Let's say each single particle composing the system, you initialize it with some specific position and momentum. Usually, you want to select a specific macro state, which is the macroscopic state of the system. That is, usually you initialize your system in order to have a specific target energy or a specific target kinetic energy, that is a specific target temperature, a specific pressure, a specific density, and so on. So usually you initialize the system by imposing some constraints, such as, for example, you choose the initial energy and so on. So once you assigned the microscopic state, that is the initial position and momentum of each particle, Then you compute the force acting on each particle, that is the internal forces, which is the intermolecular forces or interparticle forces, and in case your system is out of equilibrium, the external forces acting on the system. Once you computed the force, you update the position and the momenta via some numerical integration. I can think of, for someone who, if there is anyone expert in numerical numerical techniques, I can think of Runge-Kutta methods, for example, although usually you don't want to use those because they are quite computationally intensive. Typically, in molecular dynamic simulation, typically, not always, you sacrifice accuracy for speed, because usually you have so many particles that the error that you accumulate on each trajectory will get washed away by the interaction, by the constant interaction with the other particles. But anyway, yeah. Equilibrium.
How do you define equilibrium?
If there are, yes, yeah, because they don't, I don't think they can hear.
Do you want to speak louder?
No, I don't. So someone asked what you mean with equilibrium and I guess non-equilibrium system. So with equilibrium and non-equilibrium, you mean, let's say a system is out of equilibrium if you have macroscopic fluxes of any quantity in the system. Example, a fluid with a gradient of temperature. This system is out of equilibrium because if there is a difference in the temperature, there is a flux of energy, heat, let's say, macroscopic. Because if you go on the, let's say, on the molecular level, what you see is just random motions of atoms. So you cannot distinguish somehow equilibrium and non-equilibrium at molecular level. If you just focus on few atoms, you can see that. But if you let's say look at the system as a whole, if you can see macroscopic fluxes of any quantity, momentum, energy, mass, concentration of, in case you have different species of atoms, of particles, if you have diffusion of one type into the other one, so if this flux is macroscopically detectable, then the system is out of equilibrium. Does it make, yeah? They asked whether it's the same as a steady state. No, not necessarily. Steady state means that the system does not change its state in time. But for example, if you have a stationary heat flux, because suppose you have a fluid between two walls, two layers, and one layer is at a certain temperature, the other layer is at a lower temperature. Okay, so you have a flux of heat from A to B. Okay, it can be stationary, and you can solve this easily with Fourier laws and so on with continuum mechanics, but it's out of equilibrium because you have a continuous flux of energy. In general, you have a macroscopic flux of a certain quantity in your system, so it's out of equilibrium. This is what is called in molecular dynamics, in statistical mechanics, let's say. Now you understand why in classical thermodynamics, but now we are going to sort of, let's say, a minefield because it's they are very tricky concepts sometimes. But now you understand why in classical thermodynamics you want your transformation to be reversible, such that every time the system is at equilibrium with the environment. So the transformation is so slow that every time you are at equilibrium with the environment, because it's easier at equilibrium. For example, it might be hard to use classical thermodynamics in out of equilibrium and so on. Anyway, did I answer to your question?
Yeah, very nice.
Yeah, thanks. But it's a very tricky. There are some very tricky concepts about statistical mechanics, and so it's a good question. It's a good question. Yeah. So if you have macroscopic fluxes of any quantity, then even if you are in a steady state, then your system is out of equilibrium. And by the way, if your system is out of equilibrium, you cannot find any for those of you who are familiar with the concept of statistical mechanics, if your system is out of equilibrium, there is no hope to find the distribution function of your ensemble, either with Gibbs or Boltzmann. Usually, it's very hard, let's say. Anyway, so going back to molecular dynamics, so you integrate your equations of motion and you update the positions and the momenta accordingly. And periodically, you measure, you calculate, you measure in your system the quantity that you want to investigate. It can be the energy, it can be the pressure, and so on. So in this sense, the way we use molecular dynamics is a mean, a numerical mean, to generate random samples from a probability distribution that in which let's say that we don't know. That's why we have to use numerical techniques. Now, regarding the external field, that I mentioned earlier, in case your system is out of equilibrium, the external field can be chosen depending on the system that you want to investigate. It can be, if it's a heat flux, you can have a specific external field. If it's a shear system, you can have a different external field. So this is pretty much dependent on the system that you want to investigate. Regarding the intermolecular forces, you have sort of less options, in the sense that essentially at that point you have two options. You either use the so-called ab initio techniques, in which you solve numerically the wave function that is described by quantum mechanics of each single atom or molecule of your system. You solve this function, and from that, numerically, and from that you can compute the interparticle potential. Or you use empirical potentials, which are, of course, a simpler version of the potential described by statistical mechanics, and so you sacrifice accuracy in order to gain, for simplicity of your simulation. And there are hundreds of different empirical potentials that you can have. For example, only for the water molecules, there are probably dozens of different potentials that have been proposed in the years. But in general, now we keep it simple, because this the work that I'm going to show you is mainly methodological, so it's not related to specific realistic models. And so the easiest options are the Lennard-Jones and the WCA potentials. And that I'm going to show you in a second. How do you model? Lennard-Jones and WCA are atomistic potentials, in the sense that they have a spherical symmetry, which means that they are good for atoms, they are not good for molecules. If you want to study a molecular system, what you do is simply you create clusters of Lennard-Jones or WCA atoms, and these atoms are linked to each other, are bound to each other by some harmonic forces or by explicit constraints that keep the distance between the particles fixed, and so on. So how does the Lennard-Jones and WCA potential look like? This is the expression that you have. So first thing to note is that sigma, in this formula, sigma is the particle's diameter, while r is the interparticle distance. First things to note is that it's a pairwise potential, which theoretically is not true, in the sense that if you go for quantum mechanics, then you will, let's say, what happens is that the presence of a particle close to another one will influence its potential. And so theoretically, you should account for three particle interaction, 4 particle interaction, and so on. But as we said, this is the, let's say, the easiest way to model atoms. So we said sigma is the diameter of the particles, r is the interparticle distance. And second thing to note is that this potential is set to 0 if the distance between the particle is larger than a certain threshold. Now, depending on how you set this threshold RC, the critical radius, you can have the WCA or the Lennard-Jones. I will explain you in a minute. Now, essentially, here you have two factors, two components. You have an attractive component, which is this first power, sigma to the r, sigma to the r, sigma over r to the 12th power. This is the repulsive component that becomes dominant if the particles are close to each other. And then you have an attractive component, which is minus sigma over r to the 6th, which becomes dominant if the particles are far away from each other, roughly speaking. Now, the point in which you have the turning point, which is the minimum of the distribution that you see here, in the plot here, is 2 to the 1 over 6 sigma is the minimum, and it's the point in which you have the transition from, let's say, attractive, from repulsive potential and to attractive potential. Now, if typically in a Lennard-Jones you set the critical radius to be at least 2.5 sigma, 2.5 the particle's diameter. In this way, in a Lennard-Jones potential, you have both the repulsive and the attractive component. If you want to keep only the repulsive component, then you set the critical radius RC to exactly the minimum of this function, which is 2 to the 1 over 6 sigma. And so essentially you get rid of the attractive component. As you can imagine, WCA, it's usually much more efficient. Maybe it might be less accurate, but it's much more efficient from a computational perspective. Why? Because the shorter the interaction range, the faster the simulation, because you need to compute less pairwise interaction. And keep in mind that in a molecular dynamics simulation, the computation of the forces is by far the most expensive operation of all. Now, going to an example of what you can do with molecular dynamics simulation, I will show you a very simple system that we analyzed recently, which is this. You have WCA or Lennard-Jones fluids in fluid state, Lennard-Jones particle in a fluid state. And they are the gray particles that you can see here in the top figure. And this fluid is confined between two walls. The walls are made of particles in general of the same type. So you can either use Lennard-Jones or WCA. The two walls are kept in position by a virtual lattice that is tethering them with a harmonic force, like you see in the lower figure. Here you see the black dots is the virtual lattice that has a very ordered, essentially it's a crystal, so it's a very specific ordered position. And each side is linked to the corresponding particle by a spring. So this keeps them in position and prevents the fluid particles to escape from the channel. As you can imagine, it's a very crude model, but it's the starting point to investigate, for example, the carbon nanotube that we were discussing before, or maybe let's say the very tight interface between mechanical device in which in the middle you have lubricants, another possible application. Okay, now this is a boundary-driven system in the sense that, for example, in a system like this, you can study a Couette flow. How do you, let's say, how do you promote a Couette flow in a system like this? You impose a certain velocity to the lattice sides. Let's say a positive velocity v to the upper wall and the negative velocity v to the lower one. And so the two walls are shearing let's say, moving in opposite directions. The lattice sides are dragging the wall particles because they are linked by this harmonic force, and the wall particles interacting with the fluid particles with the pairwise potential Lennard-Jones WCA, they transfer momentum and energy into the fluid region, and they will promote the desired velocity profile. Now you can, let's say, if you allow the lattice sides to move only in the x direction, then this means that the separation between the two walls is constant during the simulation. But you can, for instance, allow the simulation to run at constant pressure, not at constant volume. In this case, you might want to, this is a possible way to generate a simulation at a system at constant pressure. You might allow the upper wall to oscillate also in the y direction, the vertical one, and you apply a constant force homogeneously to each lattice sides. In this way, if in the fluid region you have, we can say, an excess of pressure, they will push up the wall, the upper wall, and this process will stop when the pressure will match the force that you are applying on the lattice sides. So the force must be chosen to match the pressure the target pressure that you want to achieve. By the way, for clarity, I didn't plot the third dimension, but this system is in 3 dimensions. You also have the z direction, which is pointing, it's vertical to the paper, we can say.
Can I ask a question?
Yes.
Are the confines periodic?
Yes. Yes. Someone asked if you have periodic boundary conditions. Of course, in molecular dynamics, you always have periodic boundary condition. I didn't discuss about that because, of course, it's very technical and might be a bit abstract for people who are not used to this kind of simulations. But of course, if your system has a finite size in the, let's say, x direction, then you can shear the system up to a certain point, because after a while the walls will be too far from each other, because they will get far. But actually what you do is that you use periodic boundary conditions in the x and also in the z direction, but let's focus on the x direction here, which means that, for instance, if we focus on this particle here, so the last particle in the innermost layer of the upper wall, once you reach a certain threshold, which is the limit of your system in the x direction, so when you exceed a maximum allowed length, you will be remapped on the other side. So this particle, this particle will appear in the other direction. So it's as if you have a periodic system. It's as if, we can say, geometrically speaking, it's as if your system is on a cylinder. In this way, you can run the simulation for an indefinite amount of time, because you have a constant shear and the particles are being sort of replaced and remapped on the other side. Of course, this is standard practice. Of course, this must be done properly, in the sense that clearly when you have a system like that, essentially it's as if you have a periodic system, so you need to be careful on the properties that you are computing. But anyway, this is standard practice. Okay, so we run the simulation. Actually, we run 100,000 simulations in parallel, in which each of those systems is macroscopically the same, which means all the systems are in the same initial density, the same temperature, the same energy. But the macro state, the macroscopical state is the same, but they are microscopically different, in the sense that the momenta of each particle are initialized slightly differently. So in this way, you have multiple copies of your system. In this case, as I said, 100,000 copies of your system, which are slightly different, will evolve differently, but they will macroscopically evolve in the same way. And so this is a way to generate a lot of data. It's a way to generate a lot of data, to generate a lot of statistics for the quantities that you want to investigate. For example, here you see the velocity and the density profile for a system, let's say for a channel that is 16 sigma wide. So the length between, the distance between the two walls is 16 sigma. Now, from now on, I'm talking about, I'm expressing every quantity in reduced unit for simplicity, which means that in this specific case, I consider the particle diameter equal to 1. This means that the system is the separation between the wall is 16. Okay, with a shear rate gamma dot, that is the relative velocity between the two walls over the separation distance, equal to 10 to the minus 2. Again, in reduced unit, you will see what this corresponds in real units, let's say. Anyway, so I generate the velocity and density profile. How do you do that? You partition your system into the y direction, which is the direction in which you have the inhomogeneity of your system, in which you have the velocity profile, essentially, and any quantity is changing in the y direction. You partition it in slabs, and then periodically you compute the average velocity of the particles within each slab. And then you merge together all the 100,000 simulations, and you obtain your statistics. So as you can see, the velocity profile is very neat and it's essentially a linear profile. So we can say that this fluid is probably very close to being Newtonian, because a linear velocity profile is what you expect from a Newtonian fluid under shear. You can see the highly structured region in the border is the wall, because in this velocity profile, I'm accounting also for the wall particles as well. You can see here that the velocity profile is going up and down. It's because you have the wall, and the wall has specific, the wall particles have specific positions. And so the distribution of the velocity is like a delta. And the wall is, the interface between wall and fluid is marked by the dashed black line. On the bottom, you have the density profile. Again, the fact that you have a distribution in the wall region, almost like some delta functions, means that whenever you say something like that, it means that essentially you are a solid. You are in a solid state, which makes sense because the wall particles are kept in position by the lattice sides. They are not free to move normally, let's say. And that's why you see a highly structured distribution in the density profile in the wall region. You also have a highly structured fluid inside the channel. You can see that you have peaks also in the first layer of fluid particles and in the second ones, because close to the wall, due to the geometry of the system, the fluid is highly structured, and it's not a solid, because solid is something more specific, but the particles are highly ordered, we can say. But then these oscillations quickly decay, and in the center of the channel, you have a uniform distribution, which means that essentially you have a pure fluid. Now, you can also, in this system, compute the pressure, the shear pressure, so the pxy component of the shear pressure, and you follow it from time 0 to time 10 in reduced unit. Now, in time equal to, all the systems start at equilibrium, which means that at t equal to 0, the velocity of the walls is 0. Then at t equal to 0, you switch on the external field, which means you impose the velocity to the lattice sides. They drag the wall, and the wall drags the fluid. And here you can see the shear component of the pressure tensor, pxy, computed in different locations across the channel. So you can see it's computed in the middle of the wall, plane 1 and 7, at the interface, plane 2 and 6, and then in the center. By the way, this figure is merely representative in the sense that our system is composed of 4,000 particles. So it's much bigger than it appears there. This is just to show the geometry of the system. Now, as you can see, first thing to note is that all the shear computed in the fluid region, so inside the channel, they converge to the same value, which makes sense. It's what you expect from a shear, from a Couette flow, essentially. You see, after the transient, they all converge to the same value, aside, of course, from plane 1 and 7, but it's outside of the fluid region, so it's not really sheared, because it's in the middle of the wall, and you have the harmonic force that is playing a crucial role there. Another thing to note is that those oscillations are merely due to the fact that you are tethering the walls to the lattice sites with a harmonic force. So whenever you have a harmonic force, you have these kind of oscillations. They are not genuine. They are an artifact of the geometry of the system. Ideally, you don't want them. So ideally, what you want is to exclude the oscillatory behavior and just take the trend. But anyway, this is the pressure tensor. It's very nice. It's computed with the method of planes. In case you're curious, so it's a way to compute the pressure for inhomogeneous fluids, which means for fluids in which you don't have a constant pressure across the whole system. It's called method of planes and allows you to compute the pressure, any component of the pressure, Pyy, Pxx, Pxy, Pyz, and so on a specific plane. Now, here you see the slip velocity. So this is another very important quantity to measure in a system like this. The slip velocity is the difference between the velocity of the wall and the velocity of the first layer of fluid particles. So we can say, roughly speaking, is the difference in the velocity between the second peak that you see here, between this second peak here and the third peak. So the second peak is the innermost layer of the wall, and the third peak is the outermost layer of the fluid. So essentially, the slip velocity is the difference in the velocity at the interface. And usually, when you solve a Couette flow with continuum mechanics, you need to impose that boundary velocity. So you need to know that boundary velocity. As you can imagine, in this system, you make no assumptions about how the fluid behaves at the interface, because everything is generated by let's say, the fundamental dynamics of the particles. So we will see if actually you have no slip, which is a common condition that you need to impose if you want to solve a Couette flow in continuum mechanics. So if you have no slip or if you actually have slip. For example, in this case, you have slip in the transient, but then essentially the system will adjust to a condition of no slip, which, by the way, confirms the linear velocity profile that we have seen previously. Now, this is very nice. It's very interesting, but so far we have been talked in terms of reduced unit. What do they represent? When I say that I follow the system for 10 time units, what does it mean? When I say that I'm shearing the system with a shear rate of 10 to the minus 2, what does it mean? Well, if you assume that your particles are argon, and Lennard-Jones and WCA potentials are quite suitable for mimicking the behavior of argon, because argon is a monatomic molecule. I think it's spherically symmetric. So it's Lennard-Jones is suitable for simulating the interaction between argon molecules. Of course, if you ask an expert, he will tell you that no, Lennard-Jones is not good either way. It depends on how much accuracy you want to achieve, of course. This is, as you can see, this is almost a toy model. We are not discussing about realistic systems here. We are just discussing about a method that I will show you in a second. Now, if you assume that those particles are argon molecules, 10 time units is about 2 times 10 to the minus 11 seconds. And the shear rate 10 to the minus 2 is roughly 5 per 10 to the minus 9 second to the minus 1. Now, is it a lot? Is it a large shear? Is it a small shear? Well, typically in technological applications, the shear that you can encounter spans from, let's say, 0. Here I said 10 to the 0, 1, but let's say 0 to 10 to the 8. 10 to the 8 is the highest shear that you usually have in, let's say, we can say nature, in technological devices. So now we are at least 1 order of magnitude above the maximum shear that you can have in realistic systems. And not only that, but so the point is, okay, let's reduce the shear rate. Let's go for realistic shear rates. This is what you get if you set gamma dot equal to 10 to the minus 5 in reduced units. This is what you get. what you get is nothing different than random noise, because the signal is too weak, and it's cancelled by the random fluctuations that you have. By the way, the slip velocity is specifically a quantity that is extremely difficult to characterize, because it's intrinsically very noisy. Now, one possible solution is, why don't you run, instead of 100,000 simulations, you run 10 million? Of course, it takes 100 times longer. Why don't you go for a larger system? It takes longer, so it's not very efficient. Luckily, we can use this transient time correlation function method, which is this. So instead of computing simply the direct average, what we call direct average, which means you have your 100,000 systems, you compute the quantity that you want to investigate, for example, the slip velocity in all of them, and then you average over all the systems, okay? Which is this quantity here, the phase average of a generic quantity B that you want to investigate. So you replace your direct average with a time correlation of your quantity of interest and the so-called dissipation function calculated in zero. In zero is when you start the simulations, and it's when you switch the fields on, okay? Now, this dissipation function is nothing but, to put it in simple words, is nothing but the time derivative of the total energy of the system at time equal to zero. So it's even very simple to compute. More specifically, is proportional, because you have a prefactor that is multiplying the function. But for our purpose, the point is that this dissipation function is the derivative of the energy. So if you compute, so if you replace, let's say, the direct average, the simple average with this integral, what you get is this. This is an example of the application of the transient time correlation function. So this is the shear pressure pxy at the interface between wall and fluid. As you can see, and as you can see also from the previous figure that I shown you, for gamma dot 10 to the minus 2, the direct average works fine. We have seen it in the previous plot in which I shown you the shear pressure at different locations. And the direct average and the TTCF, the transient time correlation function method, are roughly equivalent. But if you go for lower shear, for 10 to the minus 3 to 10 to the minus 5, as you can see, the direct average becomes essentially random noise, no hope of getting any signal from those data, while the TTCF formalism still allows you to get a perfect signal. And by the way, the data are the same. The data are the same. So what I'm saying is that the data that I'm using to compute this direct average are the same data that enter in this formula here, are the same identical data. So essentially, it's a way to clean the signal in such a way that you can achieve a much higher accuracy with respect to simply measuring your signal and averaging over your 100,000 independent simulations. This is another example. This is the velocity profile to shear rate 10 to the minus 5. Again, you see on the left, there is no difference between random noise and this velocity profile with the direct average. It's the blue line. While if you zoom, because of course now we are way, let's say, an order of magnitude, 2 orders of magnitude better, if you zoom in the red line, you will see the linear profile in the TTCF. And again, in the slip velocity. That's the slip velocity. So again, the difference in the velocity at the interface. With the direct average, you cannot hope to achieve any result, any good result. With the TTCF, you have a perfectly clean signal. This is another, in my opinion, very interesting figure, which shows you this. So now we are plotting the signal-to-noise ratio of the direct average for the in the computation of the pressure pxy, the shear component of the pressure tensor, and in the slip velocity for various systems that we tried. You see here pxy computed. You see here the legend. Oh, I'm sorry. the legend means PXY computed with WCI particles with direct average, and then Lennard-Jones particle, direct average, and so on. Now, as you can see, and makes sense, the signal-to-noise ratio, which is defined as the value of the signal at t equal to 10. T equal to 10 here, you see. T equal to 10 is where you are supposed to reach a steady state. So it's your steady state pressure tensor, your steady state slip velocity, and so on. The signal-to-noise ratio is the ratio between the signal in t equal to 10 and the standard error of the signal. As you can see, it's decreasing for the direct average. It's decreasing up to a point in which you cannot hope to achieve any good result from it, while it's roughly constant for the TTCF, which means that the weaker the external field, so if you go for gamma dot 10 to the minus 2 to 10 to the minus 3 to 4 to 5, the weaker the external force, the weaker the signal, but also the more accurate the TTCF is, because otherwise the signal-to-noise ratio would not be constant. And so in order to test this theory, I also went for, I tried a slightly different system, and I went to very, very, very low shear rates. You can see here, I don't know if you can, maybe it's a bit small, but anyway, this is the slip velocity, in the system with a shear rate of 10 to the minus 10 on the left and 10 to the minus 15 on the right. As you can see, the direct average, again, is nothing but random noise, while you can still see clearly the signal, the transient, and the oscillations in the data computed with the TTCF method. And yeah, this is, let's say, the end of my results. As you can see, they are very, it's a toy model in the sense that we are working on the method, and we will apply this method to more realistic systems in the future. Anyway, I just gave you a very, very, very superficial overview of what molecular dynamics is. I gave you an example of what you can do with molecular dynamics, a very simple example, of course. And I gave you a bit of insight into the power of this formalism that has not been discovered by me. It has been proposed about 30 years ago, but no one applied it to the slip velocity and to the velocity profile so far. So it's a very interesting new results. And yeah, that's it. I hope you enjoyed it, and that's all. Thanks.
Thank you very much. Hello? Hello? Can you hear me? Yeah, okay. So questions, please. Yeah, Mark.
So the slip velocity presumably depends on the materials involved.
Yeah,
material.
Yeah, it depends on many. Yeah, it depends on many things. It depends on the pressure that you are imposing in the system. It depends on the type of molecules that you are using. It depends on the size of the molecules. It depends on the material, as you said. It depends on many. It depends on the density of the fluid as well.
The material I was curious about. At what level is the particular? So there's nothing in what you said, I don't think, that was apart from when you mentioned argon, I think.
Yeah.
That was particular to a specific material.
No, because this is, as I said, it's a very
Where would that come in? So supposing you wanted to model a non-Newtonian
sure.
fluid,
for example, for example, here instead of having just a single particle, a sphere, to put it in simple words, here instead of having a wall composed of fluid particles, you have a wall composed of spheres. You would have wall composed of molecules, and so maybe the molecules are, let's say, directed in a specific direction, and so on. This is what we are going to do. This is a very, 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 very simple model, very easy to model. I wrote the code to generate this in a couple of days. It's very simple. Molecules would be much harder to model, but yes, different materials would enter here in the sense that the fluid would be composed by water, for instance. So instead of having just gray spheres, you would have essentially a cluster of 3 atoms. So now there are many different, as I said, many different potentials for the water. But one possible solution would be you generate essentially you generate clusters of 3 atoms with Lennard-Jones, and the central one has a larger diameter because it's the oxygen atom has a larger diameter, and so different materials enter here in the sense that you would not have spheres in the wall and in the fluid. You would have a more complex geometry. The orientation of the molecule would matter, and so on.
So the other thing can I ask another one? The other thing I wanted to ask is, in your springs in the wall, there's some sort of stiffness then associated with those springs.
Of course.
So do the results depend on that stiffness?
They depend a lot on that.
Oh,
yeah.
Okay.
Yes, of course, there are much more technicalities behind this method. But for instance, I can just give you this. If you set the spring to be too rigid, which means that the wall is truly a solid and you don't move the wall particles at all, the TTCF doesn't work because it requires mixing to work. Now, I'm not particularly expert in the theoretical foundation of statistical mechanics, but if you have a solid, you don't have mixing, and the transient time correlation function formalism doesn't work. I tried it, it doesn't work. If you have a solid, if you put too much pressure, and so also the fluid becomes solid, it doesn't work. The stiffness plays a huge role. It also plays a role in how large your slip velocity is. Because of course, the higher the stiffness, the more likely you have let's say the particles to slide on each other. Yeah.
Okay, thank you.
You're welcome.
Davide?
Thank you. Really nice talk. Can I ask two questions? So first question is, so you've shown an example where essentially you're able to reproduce what comes from normal fluid mechanics.
You mean from continuum mechanics?
Yes.
Yeah.
So can you mention some example where you actually obtain something completely different, so that, I mean, this method is actually very useful, because if you would use normal fluid mechanics, you won't get the same transport properties or whatever.
Well, for instance, now this was just a hint, because this is in one of the, let's say, attempts that I was making when I was studying the limit of this method. You can see here, for instance, that you have slip. Now it's not a very large slip, but you can see here that it's, aside from the oscillations that sometimes it's very hard to get rid of, you can see that it's not converging to a non-slip condition. This is a situation in which you might not have a Newtonian fluid. In general, you can generate a non-Newtonian fluid with just a Lennard-Jones. It's hard, but you can generate a non-Newtonian fluid with a Lennard-Jones if you go for very, probably high pressure, I would say. But again, I didn't look into it so far, because we will go, when we will analyze with this method realistic systems. For example, the first one that we want to try is, I think, fluid water in carbon nanotube. So the walls are carbon atoms, and inside you have water. This is the first example. I can assure you that in this situation, in which probably the water is quite Newtonian, but it also depends on the condition in which you study it, and also it depends on the channel width, of course. In conditions like that, probably you don't have Newtonian fluid, and the slip velocity is extremely hard to characterize in systems like that. Yeah, but yeah, I don't have here any specific example of non-Newtonian fluid. But if you play with the parameters of the simulation, so the density of the wall, the size of the diameter of the wall particles, because the smaller the particles, the smoother the wall, you can generate high slip systems, non-Newtonian fluid, and so on. Yeah. Okay. I hope
No, thank you. Yes. And yeah. So, and the second question is why the transient time correlation function works. I mean, what is the idea behind that?
Yeah, actually, let's say I haven't told you the whole truth behind this method, because of course you want to keep it simple. Now, I prepared a couple of other slides here just to show you the method. Now, the point is this. As I said earlier, we still have time because it might take 5–10 minutes. So, as I mentioned earlier, you have your 100,000 systems independent and you average over them. Now, actually, when you want to use this formalism, from one of those 100,000 starting point, initial conditions, you generate other 3 initial conditions, specular, with these other 3 rules. What I'm saying is this, I'm trying to put it in simple words. So instead of simulating 100,000 systems, you simulate 400,000 systems. You have your 100,000 original system that are used to compute the direct average, plus you have other 300,000 systems that are similar in the beginning of the simulation, so in the starting point to the original ones, but in which, for instance, all the momenta of the particles are transformed like in the first transformation. So you take the starting point, you keep the positions of the particles the same, you invert the momenta. Or you can invert the x component of the particles. You see the second transformation, which means you reflect your system. It's like having a specular system. Or you can invert both momenta and x. You can play with this. Why you do that? Because in this way, you cancel the noise. The noise will be, let's say, if you do in this way, you are canceling the fluctuations and you are just keeping the signal, because all those transformations do not change pxy, do not change the slip velocity. So they keep the quantity that you are interested in constant, but they cancel the noise. This transformation keep all the quantities, slip velocity and the pressure tensor unchanged. Because, well, actually it's not the noise, wait, it's not the noise, it's the omega function that is identically equal to 0. This is the first point. And then, in my opinion, I have to think about it, but in my opinion, it's also related to the noise. Now, the first advantage of this transformation is this. So if we go back to the formula here, now the only way this integral can converge is since after, let's say, at t going to infinity, clearly, the correlation between b and omega 0 decays, which means that this product can be factorized into average of omega 0 and average of b, of t, for time going to infinity. Now, there is a problem in the sense that omega 0 is meant to be equal to, the average value of omega 0 is meant to be equal to 0, because at equilibrium, on average, the energy is conserved. Now, in your simulations, omega is statistically speaking equal to 0, but not strictly speaking, which means that your data might show, let's say, an integral that does not converge, because omega 0 is not strictly equal to 0, even if it should be. Okay. Now, these mappings allow you to, you can check, and I will show you also the expression of omega 0 now. These mappings ensure that the average of omega in 0 is identically 0. Not just on average, is identically 0. And so this improves the statistics. Now, this is one advantage. In my opinion, it's also, but I have to think about it because I'm still, let's say, exploring this method. In my opinion, it's also related to the noise, in the sense that you're canceling the noise. Now, why don't you do that with the direct average? If you do that with the direct average, in the sense that you average over all the mappings as well, you would have the same results here for the very first moments of the simulation. You would have a very clean signal in the direct average as well. You would have it. That's why I believe that it's related to noise. The problem is that with the direct average, the correlation between these mappings rapidly decays, and then after very few time units, it's as if you have only 4 times the number of samples, which is way not enough, which is not enough at all to generate good statistics. While with the correlation integral, you can keep this correlation for much longer, which allows you to reach the steady state or to reach a good, let's say, signal for long enough to, let's say, to have a good result. But theoretically, these mappings would improve also the statistics of the direct average. The problem is that the decay is so rapid that you can't do anything with it. That's why I believe it's also related to the noise cancellation, but I have to think about it a bit more. I hope I have been clear. I was a bit long.
Yeah, okay. So then we should finish. Already a little bit, several minutes behind 3. So then once again, thank you, Luca.
Thank you for inviting me. Thanks. Thank you for inviting me.
And Luca will be here today and could be tomorrow morning
as
well.
That's right.
So if you have any questions to him, please. And I understand. Okay, could you stop recording? Could you start?